Okay, so the simple queuing algorithms, first in, first out, and fair queuing, helps in providing congestion control mechanisms or in a network, in addition to the end-to-end control congestion algorithm. But we also need to provide some sort of assistance in congestion avoidance. Okay, so we also need to see how the queuing disciplines can provide help in congestion avoidance. So up till now we have discussed one way to avoid congestion, and that is, yes, that's right, that is to avoid congestion by the ends. So we have discussed one mechanism up till now, and here we talk about avoid congestion from the ends, where the sending machine slows down the sending rate of an application avoiding a congestion. And we have seen this in the TCP's congestion control mechanism, that after reaching the slow start thresholds, we always start incrementing the congestion window size additively in order to avoid congestion. But there are other ways as well in which we avoid congestion, and it has to do with something with the queuing discipline, and it is called active queue management. AQM. So in addition to traditional end-to-end congestion avoidance, or where the end machines are avoiding congestion, we can also take help of active queuing management to avoid congestion. So the idea of active queuing management is to put additional functionality into the routers. Why? To assist the end nodes or machines in the anticipation of the congestion. In the anticipation okay, so yes, the end machines avoid congestions, and if a congestion happens, we will be able to identify when a packet has dropped or a timeout has occurred, right? So rather than waiting for a packet to be dropped or receiving triple duplicate acknowledgement, why not route it to assist end machines in the anticipation of the congestion? There are following different active queue management techniques, algorithms that we can discuss. The one is called active deck bit. Number one is deck bit, that will have RET, random early detection. By the way, when you create a node in NS2 in your lab experiments, so you always associate a type of queue with the node. Either it's a drop tail or it is red, which is random early detection. So we'll talk about deck bit and red in detail in a minute, right? And then there's another active queue management mechanism known as explicit congestion. Number three is explicit congestion notification. So rather than putting the responsibility of congestion control and avoidance at the end machines, why not the router should also assist in the end machines in the anticipation of the congestion. So let's talk about first the deck bit. Okay, the deck bit was developed for the use on digital digital network architecture. DNA. Right. So a router explicitly notifies the end node. Means the destination, right? So what it does is basically that it how this is implemented. This notification is implemented by setting binary congestion bit in the packet. And that's why we call it DEC bit, right? So by setting a binary congestion bit in the packet is forwarded to the destination. The destination host then copies this congestion bit into the acknowledgement to notify the source that there is a possibility of having a congestion and it needs to slow down the sending rate, right? So the next question is how a router or when a router sets a congestion bit in the in the packet header, right? So a router set this bit in a packet if its average queuing length is greater than or equal to 1. So if the average queue length is greater than or equal to 1, then the router will set the congestion bit to 1 at the time packet arrives. Okay, so it's important to talk about the average queue length. Now let's try to understand this with the help of this diagram, where in this diagram the queue length is represented as a function of time, and then we have two transmission cycles where we have, say, this curve represents previous cycle, and this curves represent the current cycle. So this is the previous cycle, and here it represents the current cycle. Right, and say so this is the current time. Okay, and then we can calculate this average interval, or you can say that this is averaging interval. Which is obviously the average interval or the average queue length is measured over a time interval that spans the last busy cycle plus the idle cycle and plus the current cycle. So this means, as is also evident from this diagram, this is the average queue length is, so average queue length is basically is measured over an interval that spans last busy cycle plus the idle, which is, by the way, here up till here we have the last busy cycle, and here is the idle cycle. So this represents the last busy cycle, and this value is from this point to this. This represents the idle cycle. Idle cycle is the one where we are not sending anything on the network, and this represents what? This represents the current busy cycle. Okay, so so the average queue length is last busy. So this time plus idle, this free time where we are not sending anything on, where there are no packets in the queue, and plus the current plus the current busy cycle. Right. So what it does is basically it calculates the area under the curve and divided by the time interval to compute the average length. Right. So how the average length is calculated, considering the last busy plus idle plus the current busy cycle, is that it calculates area under the curve. And then it divides it by time interval to compute average queue length. Right. So a queue length of 1 means to optimize the power function. Remember the power function we represented as a ratio of throughput to delay, right? So the this means a queue length of 1 means what? Means it seems to optimize the power function. Right. So it's basically a trade-off between the significant queuing. So we can call it a trade-off. It's a trade-off between significant queuing. This means what? This means significant queuing means what? Significant queuing means higher throughput. And increased idle time. And what do you mean by this idle time? Means lower delay. Okay, so a queue length of 1 means we are optimizing the power function, and it's basically a trade-off between the significant queuing, which will result in higher throughput and increased idle time. This means lower delays, right? So we can understand it with the help of an example here. Understand this with the help of example. Let's assume that less than 50% of the packets had the congestion bit set. You can have the bit set. So what does this mean? This means then source increases its congestion window by 1 packet. So let's assume there's a scenario where less than 50% of the packets had this bit set. The source will increase its congestion window by 1 packets. And what if more than 50% of the packets had this bit set? Then the source decreases its congestion window to 0.875 times the previous value. All right. So this means what? So, by the way, so this means the increase by 1. So the increase by 1 and increase by 1 and decrease by 0.875 is because of its similarity to additive increase and multiplicative decrease. Right, because the same was happening in additive increase and multiplicative decrease. So on every successful, remember in congestion avoidance, we were increasing the window size by 1, and whenever we observed congestion, so we decrease this window size multiplicatively with a factor of 0.875. So same is the case in the deck bit, right? So what do you think? What are the problems with the deck bit, right? So the problem with the deck bit is that if you want to include it with the typical congestion control mechanism, here we need to send explicit congestion notification by the routers, and then so there can be another way where we can implicitly notify a sender in advance about the congestion anticipation, right? Or in order to avoid congestion, and for that we have to discuss the second active queuing management algorithm known as random early detection. RED. RED was proposed by Sally Floyd and Ben Jacobson. Okay, this random early detection differs from DECBIT in two major ways. Number one, rather than sending a congestion notification, RED implicitly notifies the source of congestion by dropping one of its packets. So RED implicitly notifies the source of congestion by dropping one of its packets. So there are no specific congestion bits are used to indicate a congestion. And the second thing is RED decides when to drop a packet and what packet to drop based on a drop probability, right? So if it has to do packet dropping, then the question is how RED decides, for one, when to drop a packet, and number two, which packet to drop. So these are two important decisions that we have to make in RED, and this happens with some drop probability. So to drop a packet and which packet to drop is happening with some drop probability. Whenever the queue length exceeds some drop level. So this means the routers using RED maintains a certain drop level, and whenever the queue length exceeds the drop level, we drop a packet based on a drop probability, right? And that's why the idea is called. That's why this idea of dropping packets early with a probability is called. The idea is called early random drop. Early random drop. Okay. So, so in order to understand random early detection, it's important to understand the computation of average queuing length, because we will drop a packet with certain probability if it's exceeding the queue length. So let's talk about how we can compute the average queue length. So computation of average queue length. Okay, so the queue length or RET calculates or computes the average queue length using this formula. RET calculates the average, computes average length using this formula S. So average length is equal to 1 minus weight into previous value of average length plus weight into sample length. Okay, so we use this formula to calculate what? To calculate the average length, and you can clearly compare this formula with the calculation of sampled RTT, right? So there we also calculated the average value of running value of sample RTT in a similar way, right? So in this example, the weight is between 0 and 1. The value of the weight is between 0 and 1, and the second parameter that we are taking into consideration is the sample length, and sample length is the length of the queue when a sample measurement is made. Is the length of the queue when a sample measurement is made. Let's try to understand this with the help of an example. That why do we need to have the average length into consideration? So let's try to understand the need of having this average queue length with the help of this scenario. So what this figure represents is that the queue length is represented as a function of time, and usually we have a burst of traffic in the network in clusters, so there's a possibility that the queue length increases for some specific amount of time, and then we have done with transmitting all the packets in the queue, and again we have a burst, and then we're done with the transmission of the queue, and the queue length is again reduced. Then we have again increase in the traffic, or we have traffic burst here. So what is happening here is that we have a very inconsistent changes in the queue length, obviously because we have traffic burst. So instead of using this value for the calculation of the probability to when to drop a packet or to calculate an average queuing length, so queue length, why not to take an average queuing length into consideration, which is more smooth for calculating the average, for calculating the probability of drop. So in order to calculate the average queue length, the RT has two thresholds. So how we will calculate this average queuing length? For that we have in RT, random detection has two two queue length thresholds. Okay, one is called minimum threshold. And the second is called let's try to understand this with the help of this queue diagram. So let's assume that it's a queue that is being maintained by RED. Okay, and this value here, say, identifies the minimum threshold. And say this value here, somewhere here, identifies max threshold. Right, so the average queuing length will be somewhere here. Right, so in order to calculate average queuing length, we have two thresholds. We have a minimum threshold and we have a maximum threshold. So we try to understand how this average length is computed using minimum threshold and maximum threshold values. So how RED calculates the average length with this minimum and maximum threshold. So if average length is less than equal to minimum threshold, then obviously queue the packet. So it's somewhere here less than the minimum threshold, so we will keep queuing the packets. If minimum threshold, or if it is between the minimum threshold and maximum threshold, then we have, if it's somewhere here, which is in the diagram at the moment, in the figure at the moment. So if it's between the minimum threshold and maximum threshold, then this means we have to calculate probability P, probability P means drop the arriving packet, right? Probability with probability P, right? And the third condition is that that if max threshold is less than equal to average length, drop the arriving packet. Right, so if again we look at this diagram, so if this means if the average length is less than this minimum threshold, we'll keep queuing the packets, And if it is between the minimum and the maximum threshold, we'll always calculate a probability with which we will be dropping the packets. And if this average length is somewhere greater than this maximum threshold, obviously every packet that is arriving at the router in this queue will be dropped, right? So the probability of dropping as a function of average length, but situation is actually a little more complicated. So let's try to understand this drop probability with the help of this figure. So let's assume that this probability of drop is represented as a function of average length, right? And we have obviously two thresholds. We have min thresh, and then we have the maximum threshold. Right, and then on the probability we have max P, maximum probability P, and then we have probability 1. Right, so what happens here is, just to understand it, that we increase slowly the probability of drop, and when it reaches this maximum probability, we start dropping all the packet, and if still the average length is greater than the maximum length, maximum threshold, all the packets will be dropped. So this means, though we are representing the probability of drop as a function of average length, but the situation is actually a little more complicated, right? Because P is a function of both the average length and how it has been since the last packet was dropped. So it's more complicated than this simple representation of drop probability as a function of average length. Why? Because the probability P is a function of both average length and, importantly, how long it has been since the last packet was dropped. Because this will help us in order to make sure that the packets are not dropped in clusters. Because if this is happening, that our packets are dropped in clusters, this means the sender will again go back to slow start phase. So this we don't want using this random early detection algorithm. So what we do basically is we calculate the probability in this way. Temp P is equal to max P probability into average length minus minimum threshold value divided by maximum difference of these two thresholds, maximum threshold minus minimum threshold. Right, and then this temp P is used to calculate the drop probability P. So P is equal to temp P divided by 1 minus count into temp P. Right, so here this temp P is the variable that is plotted on the y-axis in our diagram. So temp P is is the variable that is plotted on the y-axis. Okay, and the count in this count, we are familiar with all the other parameters, and the count here keeps track of how many newly arriving packets have been queued, not dropped. So obviously this will help me to identify how it has been doing since the last drop. So if P increases slowly as the count, P obviously increases slowly as the count increases, thereby making a drop increasingly likely as the time since the last packet drop increases. So it's very important to note that P, the probability increases slowly as count increases. Why? Because the count is representing that how many newly packets have been queued without a drop, right? Thereby making a drop increasingly likely as the time since the last packet last packet drop increases. Right. So this makes us to understand this important point that this makes closely spaced drops less likely than widely spaced drop, right? So extra step in calculating this P is to avoid drops in cluster. So this extra step in calculating this, P is to avoid drops in clusters, right? So why we want to avoid these drops in cluster? Because if this happens, the center will result in, this can result in, if this happens, this can result in slow start at the ends, right? And we do understand what we mean by this slow start, because obviously this will then slow down the sending rate, So let's try to understand this with the help of an example to see how RED will behave considering this diagram. So let's assume that we have a max P value of 0.02. Let's try to understand this with the help of an example. How does it work, right? So max P is equal to 0.02 and count is 0. So if average length, if let's assume if average length were half between the two thresholds, which is the case over here in this diagram, right? So let's assume if the average length were half between the two threshold values, then temp P and the initial value of P would be, so then obviously temp P and initial value of P would be half of max P. What is max P? 0.02 or the half of max P is 0.01. So, so what's the scenario? We have a scenario where the max P is 0.02 and the count is 0 and the average length is between the two thresholds. Then the value of this temp P and the initial value of P is half of the max P or 0.01. So if an arriving packet, if a new packet arrives, obviously there are 99 in 100 chances that it will get into the queue at this point, right? But P is what the P is. What is happening here is that P is increasing slowly, right? And let's assume that it has been a case that there. Let's assume that by the time 50 packets have arrived, let's assume by the time 50 packets have arrived, without a drop. So P would have reached to, P would have reached to 0.2. So this means P would have doubled. This means what? This means this value is 0.02, which is the max P, right? Now, in the very unlikely event that 99 packets arrive without a loss, P reaches 1, right? So if we assume that there has been no packet drop here, let's just assume it, and this means now P is at 1. This means what? Every next packet will be dropped from the queue, right? So here we were assuming that max P is 0.02 and the queue length is between these average length is between these two minimum threshold values, and we are slowly increasing its size, and by the time when we have 50 packets without a drop, we assume that the max probability or the probability is equal to max P, which is 0.02. And if we still believe that there has been no drop, which is very unlikely, this means the probability will become 1 in this case, and every other packet will get dropped from the queue, right? So, so this means if we want to conclude that the RED ensures a roughly even distribution of drops over time, and it's very important. So RED, random early detection, ensures a roughly even distribution of drop over time, right? And why this is important? Why this is important? Yes, it's important because this will make sure that drops are not happening in clusters, and if drop, on contrary, if drop happens in clusters, this means the center will start into a slow start. And this concludes our today's lecture. So today we'll talk about the different resource allocation mechanisms. First, we establish a case that we need to have resource allocation mechanism in addition to typical congestion, end-to-end congestion control mechanism. And then we started discussing the evaluation criteria of different resource allocation mechanisms, and then we tried to understand the different service models and the taxonomy of congestion control algorithms, and then we discussed the most important part of congestion control, the most important part of resource allocation mechanism, the queuing disciplines. Then we discussed the two very common queuing algorithms, first in, first out, and fair queuing. And then we also talked about that we can enhance, so we can force the routers or the network elements to assist in congestion avoidance, and for that we need to understand active queuing, active queue management, AQM, and in active queue management we talked about dead bit and random early detection. So this concludes our today's lecture. Thank you very much. Allah Hafiz.